Okay, this is your question of the day. You're going to go ahead and write it in your notebooks. Make sure that you start a new page for this. This is going to be standard 8.PS 4.1. And basically it has to do with waves. So the first question is, what is a wave and are they all the same? So with are they all the same, please don't just write yes or no. Explain to me why you think that they are or why that you think that they are not. So what is our next standard specifically? If you look at the top of your new colored sheet of paper, you should see that we have PS 4.1, where it says develop and use models to represent the basic properties of waves, including frequency, amplitude, wavelength, and speed. And I am sure you have heard all of this from last year. I'm hoping you have, and it all is coming back to you now. We'll do some things with Slinkies and some online simulations and those sorts of things, and look at exactly how we can figure these things out without just being given the information. So let's go ahead and get started. What is a wave? The answer to your question of the day, basically, we'll talk more about this as we do a formal introduction to this unit. But all of these pictures are different types of waves. So the typical wave that you think of in the ocean may have been the first thing that came to your mind, and that would be my first thing too. But if you're listening to me right now, then you are definitely having sound waves. And I showed you two different types of sound waves, the type of that would be produced with a guitar versus a cymbal, and how very different they look. And so why some people are, of course, are going to sound differently in their pitches and their not volumes, but in their pitches. All has to do with the different properties of those waves. Types of seismic waves. I'm sure you have talked about this last year as well, and we're going to do the same thing as we look at this more closely as we talk about earthquakes and how they are made and the way that the waves affect the land. And of course the water too with tsunamis. And then on the far right hand side here with the electromagnetic spectrum, we can see that we have many different types of waves, from a microwave, a radio wave, infrared waves, visible waves that we are actually able to see right now with ultraviolet rays from the sun, X-rays, gamma rays. Okay, all of these are able to be produced of course from the sun itself, are transfers of energy, and that is what all of these have in common. Okay, it's a disturbance that transfers energy, and so it's some kind of a movement, vibration that has caused molecules to move from one place to another. And so those molecules vibrating are causing these different types of waves, whether it is a sound wave, an earthquake wave, or whether it is a light wave. And so when we look at different types of waves, we're looking at the fact that we could either have a mechanical wave, like we see with a wave itself, a plucking of a guitar string, the actual mechanics of making it move. I'm talking right now, and so I'm making my voice move and have that ability to, you think about mechanical energy, and that's what I think about with the mechanical wave. So when we look at these mechanical waves, we are looking at a disturbance that is traveling through a medium. And when I say a medium, I'm looking at a form of matter, like a solid, a liquid, or a gas. And so we're talking about a wave in the water. And so it is actually vibrating the water molecules. When you hear my sound coming out of my voice right now, then I am having those vibration of the air in front of me, and it's pushing towards your ear. And so we look at these different types of waves, and it could be traveling through a slinky as a solid. So that's what we talk about as the medium. Is it moving through air? Is it moving through the water? Is it moving through that slinky that I have on my desk? The other thing about mechanical waves is that they cannot travel through a vacuum. So why there is no sound in space is because of that. Space is that idea where there are so few far in between molecules that there's just no vibration to take place. And therefore, those sound waves are having a very difficult time. And it's not just a sound wave, but any form of a mechanical wave. On the flip side of things, we have electromagnetic waves, and if it weren't for these, we would be a very cold planet with no light, okay? Because electromagnetic waves can travel through any medium, solids, liquids, or gases, but are more importantly able to travel through that empty space, that vacuum that we are thankful for, because, like I said, we would be very cold. So, what is that medium? I want you to make sure that you have written this down as well. It is a type of material through which a wave travels. So you're going to hear me use that word a lot, and I want you to be able to be familiar with what I'm referring to. So the solids, the liquids, the gases, what is it that that material is capable of moving through? And mechanical waves versus electromagnetic waves are very different in that fact, which is, like I said, why we can't hear sound. Okay, so two types of mechanical waves. We have a transverse wave that you see here at the top of the screen, and it should be in animation mode, but I don't see it moving, unfortunately. There it goes. So we have a transverse wave, and as you can see, it has an up and down movement compared to a longitudinal wave that is going to be sort of from side to side. And if you think about a transverse wave, it looks a lot like a wave in the ocean. And that's really what we have. We have a type of a light wave that it can be moved this way. Ocean waves can move this way. But basically, transverse waves are going to be in this, what the official definition says, movement that is perpendicular to the wave direction itself. Okay, so we're talking about it being at a right angle. And so when we talk about it being at a right angle, as you can see, I have drawn these arrows to show you where, we have this movement up and down. And when it moves up and down, we basically are looking at a transverse wave. There is a right angle, okay? So right here, you can see this right angle to the direction. So this is the direction that it's moving, and this is the up and down movement, thus giving me the perpendicular to the wave direction. And we remember, we're talking about the particles here. So the particles are actually this rope or slinky, whatever this picture is representing. So we're talking about the particles in that medium moving in that direction. That's what we have to think about when we hear that word medium. Okay. On the flip side of things, we have a longitudinal wave, and of course you can see the longitudinal wave moving from side to side. So when we talk about this, they're saying that they move parallel, which means with the wave direction. So if we had a slinky here, this is very similar to what it would be if we had parts of the slinky really close together, and then think about how the wave travels through. This is exactly how sound waves are traveling. They are compressing in some places and spreading out more directly. Okay, so I have drawn some arrows here, and I sort of want you to do the same thing with your pictures on your paper. Keeping in mind, remember that parallel is going to run with, this is the direction of the wave, and of course that is the direction of the movement of those particles as well. So they're moving together basically. And IE just means, for example, if you're not familiar with that, it's just a shorter way of writing it. So for example moves back and forth instead of the complex way of saying parallel to the wave action. I do need you to know the more complex, but I also want to give you a reference idea of what it actually represents. So we're still talking about a transverse versus a longitudinal wave. Typically when we're trying to describe a transverse wave, we have all the same opportunities with wavelength and frequency and amplitude, but a couple of things are a little bit different because of their movement. And with the transverse wave moving up and down, we will consider these things called crests that are the highest point of the wave. And like I said, you guys are probably very, very familiar with this because of last year's lessons. And then at the very, very bottom part of a wave is what we consider to be a trough. And it looks much like a animal would drink out of a drinking trough. So that is how we describe a transverse wave, only because of that movement up and down. We can't describe a longitudinal wave that way because there is no movement up and down. This movement is parallel and goes from side to side. So when we talk about these kinds of descriptions, we are looking at one way of describing it, a compression. And here with a compression, particles in the medium are really close, or they are being pressed together. That's a good way to try to remember that, compression, being pressed. So where the particles are really, really close together, like you see down here, these are of course going to be your compression. And here you have an example of a compression. And here, I wanted to show you this too, because this is what the air particles look like, and they're really, really, really close together. That is a high density amount of particles. High density meaning a lot of them. And so where we have those areas where there's a lot of particles, a lot of slinkies right together, or a lot of air particles, whatever that medium might be, that is a higher density. And thus, that gives this a way to describe this kind of longitudinal wave. However, where they are not closer together, we are calling these rarefactions, okay? Rarefactions are going to be where the particles in the medium are farther apart. So I'm going to use a separate color here. And when I talk about rarefactions, I am looking at the idea of these further apart places in the medium. So when I'm thinking about this slinky here, where they are further apart, if I'm coming up here and looking at these areas right here, these are the rarefactions. Those particles are in a lesser amount, not as many air particles, not as many little slinky parts there compared to the areas where the compression takes place. So just a way to describe types of mechanical waves, whether it's a transverse or a longitudinal. A lot of times these work together, and so this is what this is a picture of, is just trying to explain the two types of mechanical waves that we do have, and therefore looking at it all combined together in this one guitar. So, you know, the guitar itself, of course, I'm looking at a transverse wave right here, okay? And as we have this transverse wave of the plucking of the guitar string, there's actually that vibration of the median of the guitar string itself. And what we end up with, of course, we can see over here that we then have a longitudinal wave where we end up with this compression and rarefaction area, and that is going to give us those sound waves and vibration of those air molecules once that string has had a longitudinal movement. So we look at this area of really high density, and I want you to label this on here as well. We have these higher densities where basically we have a compression, and I'm just going to put COMP there for compression. Every place that you see these higher amounts of air particles is where we have a higher amount of compression. And this is going to become really important later on, this idea of density. I'm just introducing it right now to get you familiar with it. Then in the areas where we have lower densities, this is going to be, and I'm just going to abbreviate this, rare for rarefactions, how we end up with these areas where the particles are not moving as much. But remember, they are simply moving through the air, pushing the air particles closer together, and then of course where they're not closer together, they are going to be further apart in these rarefaction areas. So key idea here is wherever you have rarefaction is typically where you have lower density of your particles or of your simple slinky movement, whatever it may be. Wherever you have your higher density is where you're going to have your compressional areas. That is extremely important to remember, okay, for later lessons.